Hello and welcome to water quality. In this video, I'm going to go over the caustic alkalinity endpoint derivation. This represents the point at which essentially all of the hydroxide has been converted to water, and essentially all of the carbonates are still present as carbonate, and they haven't yet been converted to bicarbonate or carbonic acid. And so I want you to think about this as a titration that you would do in the lab where you have a natural water sample and it contains carbonates and no other significant weak acids. And first we're going to do a charge balance before any acid is added to the sample. Okay, so on the positive side, we'll have the conservative cation charges, and I'm going to put a 0 subscript to represent that these are the CCCs before the addition of acid. And then I also have the hydrogen ion. On the negative side, I'll have hydroxide, also bicarbonate, carbonate, and the conservative anion charges. And again, I'm going to put a 0 subscript to represent that these are before the addition of acid. So essentially what I've done here is to derive the alkalinity equation. And I can call this alk, and I'm going to put a subscript old. So subscript old to represent before the addition of acid. And this is equal to the imbalance in the conservative charges, so the conservative cation charges minus the conservative anion charges. And then this will be equal to kind of the familiar definition of alkalinity, which includes bicarbonate, carbonate, hydroxide, and hydrogen ion. Okay, next I'm going to add acid until the alkalinity is to the point where it has 2 CtCO3 equivalent of acid neutralizing capacity, which is what's needed to go all the way from carbonate to bicarbonate, and then all the way from bicarbonate to carbonic acid. So my new charge balance is going to have all the same things as before, but now I need to add a chloride ion to represent the acid that's added during the titration. So I have the CCCs, same as before, and then the CACs, and I have my initial CACs, but then I also need to include the chloride that's added with the acid addition. And so this new alkalinity, and I can call it that actually, I can call it alk new. So after the addition of acid is going to be equal to 2 CtCO3. And I still have the same alkalinity expression. Oops. Bicarbonate only gets one charge. And a potential source of confusion here is that these equations look the same before and after the addition of acid, but the pH is going to shift, which will cause the concentration of all the carbonate species to shift as well. Okay, so the next thing I'm going to do here is to make a substitution with the CtCO3, and I will put in the CtCO3 equation, and it's 2 times CtCO3, so I'll put 2 times this, so it's 2 times carbonic acid, 2 times bicarbonate, and 2 times carbonate. And then nothing changes on this side of the equation. And so this all stays the same. And now I can go ahead and start canceling things out. So for example, my 2 carbonates cancel out on both sides. One of the bicarbonates cancels out, and that's it. So I'm going to rewrite this. Let's see. So I've got the only thing that I'm going to keep on the right side is the hydroxide. And then on On the left side, I have two carbonic acids, and then I still have a remaining bicarbonate. And then I'm going to put the hydrogen ion over here so everything's positive in the equation. Okay, so now I have actually a proton condition for the caustic alkalinity endpoint. And this is something that I can find on a log C pH diagram, which I have down here. So I'm going to go ahead and move this so that we can look at it while we're looking at the graph. Okay, and get my pen back. And let's go ahead and look at this log C pH diagram that I've provided. And in my example, I'm using a CtCO3 of 10 to the minus 2.5 molar. And so if your CtCO3 is different, this whole family of carbonate species lines is going to shift up and down, and your crossing points will move around a little bit. Okay, so let's go ahead and find this point on the graph. So I've got my left-hand side and my right-hand side. And on the right-hand side, it's pretty simple. I'm going to follow the hydroxide line all the way down. And on the left-hand side, I'm going to follow the dominant species. So initially, it's hydrogen ion, and I'm just following right above the line. Because this is a log graph, the sum of these things is kind of distorted by that log scale. Okay, so I've got the hydrogen ion being dominant, then it shifts over to the carbonic acid, and then it shifts over to the bicarbonate ion being the dominant species. And then these two things come together, and I can see my crossing point is right here. So this equation is satisfied at about a pH of 10.8. And that is my endpoint for the caustic alkalinity.